right, so we are on page 23. We're in section 9.7 under checking for normality. So all of the tests that we have discussed so far in this chapter 9, they have assumed that the sampling distribution is normally distributed. This assumption is often quite reasonable because the central limit theorem demonstrates that the sampling distribution will be normal if the population is normal or if the sample size is sufficiently large. So anytime that you suspect that your variable is actually an average of lots of different things, there's a pretty good chance that it will be normally distributed, or at least close enough to normal that you can get away with using the t-test. However, we can't always be guaranteed those conditions, and so there will be quite a few ways in which you might end up with variables that are actually highly non-normal. So for example, anytime you think that your variable is actually the minimum of lots of different things, there is a very good chance that it will end up quite skewed. And in psychological research, your response time data would be a really good example of this. So if you suppose that there are a lot of things that could maybe trigger a response from a human participant, then the actual response will occur the first time that one of these trigger events occurs. So this means that response time data are systematically non-normal. So if normality is assumed by all the tests and is mostly but not always satisfied by real-world data, then how can we check the normality of our sample? So in this next section, we're going to discuss three methods. We're going to discuss histograms, QQ plots, and then the Shapiro-Wilk test. So the most straightforward approach to evaluating the normality of our sample is to construct the histogram like we have done in previous sections and then just visually inspect it. So by plotting the frequency of data points within these specified intervals, the histogram will provide the really excellent visual representation of the shape of your distribution. And to assess for normality, you're going to be looking for that bell-shaped curve that is symmetric around your mean. So this classic bell curve indicates that the data follows a normal distribution, with most values clustering around the central peak and then fewer values appearing as you move away from the center. So when you use the histogram to evaluate normality, again, it is important to consider the sample size and the bin width. A larger sample size generally will provide the more accurate representation of your underlying distribution, reducing the impact of any random fluctuations and outliers. So the choice of bin width can also significantly affect the appearance of the histogram. If you have too few bins, that would oversimplify the data set, while too many bins can appear really noisy and fragmented in your visualization. So a good rule of thumb is to experiment with the different bin widths to find the one that will best reveal the data's true structure. Moving on to page 24, while a histogram can give a good initial indication of normality, it is often useful to complement this visual inspection with formal statistical tests and other graphical methods. So the Shapiro-Wilk test, for example, is a widely used test for normality, and it provides a p-value which would indicate whether the data significantly deviates from a normal distribution. Another useful graphical method is the QQ plot, which compares the quantiles of the data to the quantiles of the normal distribution. So now we're moving into 9.7.2, and we're going to briefly talk about the QQ plot in addition to the histogram. So one way to check whether a sample violates the normality assumption is to draw a QQ plot, which is the quantile-quantile plot. This allows you to visually check whether you are seeing any systematic violations. So in this quantile-quantile or QQ plot, each observation is plotted as a single dot, and the x-coordinate is the theoretical quantile that the observation should fall in if the data were normally distributed, with mean and variance estimated from your sample. And then on the y-coordinate, that would be your actual quantile of the data within the sample. So if the data are normal, the dots should form a straight line. So for instance, let's see what happens if we generate data by sampling from a normal distribution and then drawing a QQ plot. So the results that we're going to observe are going to appear in figure 9.17, and as you can see in this figure 9.17, these data, they form a pretty straight line, which would be no surprise given that we sampled them from a normal distribution. In contrast, we're going to take a look at the two data sets that are shown in figure 9.18. So the top panels of 9.18 show the histogram and a QQ plot for a data set that is actually highly skewed. And we can see in this figure 9.18 with the QQ plot that it actually curves upwards. The lower panels show the same plots for a heavy-tailed or a visualization that is showing high kurtosis in that data set. And in this case, the QQ plot flattens in the middle and then it curves sharply at either end. So so again, if you view figure 9.17 and you look at the panel A, you're going to see on page 24 the histogram, and then you're going to see next to that in panel B, you're going to see the QQ plot, and this is for normal data. So we're going to see the normally distributed sample that has 100 observations in figure 9.17, and then we could take a really easy Shapiro-Wilk statistic within our JASP software, and when we do that, we can see that our value for the Shapiro-Wilk statistic associated with the normal data is that our value W, big W, equals 0.99, which indicates that there is no significant departure from normality that was detected, and a p-value, the p equals 0.73. So we'll run through really quickly how to do the QQ plot in JASP. So we're going to use the Zeppo CSV file. So let's go ahead and open that up. So here's our JASP. It's ready to go. I already loaded Zeppo. And again, we're going to first use the descriptive statistics setting. So we open up descriptives and we choose descriptive statistics, and we're using the Zeppo file, and we're going to move our X to the variables box. we're going to allow JASP to calculate our mean, which again we remember was 72.3, and our standard deviation was 9.521, with a minimum of 50 and a max of 89. We had 20 values reported. And then we're going to go under basic plots. So let's look here. We're going to go under basic plots. Okay. And we're going to check the box for a QQ plot. We're going to check out that visualization. So again, this result that we get should be similar to what's plotted in figure 9.19. And we should observe that the dots are all very close to the line that was drawn, which tells us that the distribution is approximately normally distributed. So let's go and look at figure 9.19, which is on page 26. And again, we can verify that our QQ plot that we constructed is exactly the same, with our 20 data points, our mean of 72.3, our standard deviation of 9.521, min of 50, max of 89. That looks great. And then we're going to go back to page 25 in our chapter 9, and we're going to observe on page 25 figure 9.18, where in the top row we can see panel A has a histogram, and hold on one second, I lost my page. Let me go back to page 25. So on page 25, panel A, we can see the histogram. In panel B, we can see the QQ plot, and we have to also examine that against panel C and panel D. So let's take a look here. So panel A is showing us our data set where we have the right-tailed positively skewed data, and we can also observe what the positively skewed QQ plot would look like in panel B. And then we can see that that QQ plot, it does curve upwards. And then in the bottom row, we can see panel C and D, and this shows the same plot, but for the leptokurtic data. Again, those observations are different. They're showing the sample of 100 observations of data. And we can note that in the panel C and panel D, we have the QQ plot that looks flattened in the middle, and then we can see that there is a sharp curve on either side of that flattened QQ data. And then we can also see in panel C that this is the example of the leptokurtic data set, right? So that really tall middle of our curve. And so let's move to page 26. We already looked at our QQ plot that we made for the Zeppo file. Now we're going to move to page 27, and we're going to go and talk about the Shapiro-Wilk test. So here we go. So histograms and QQ plots, they do provide a nice way to informally check the normality of our data, as we were just talking about, but sometimes you want to do something that might be a little bit more formal, and that's where we would use the Shapiro-Wilk test. So that's why we have this slide. What is the Shapiro-Wilk test? And so the Shapiro-Wilk test, it tests the following hypotheses. So our null hypothesis would be, in the population, the distribution is not different from a normal distribution. And for the Shapiro-Wilk test, the H1, or the alternative hypothesis, is that in the population, the distribution is different from the normal distribution. So the test statistic that it calculates is conventionally denoted as capital W or big W, and it is calculated this way. So on page 27 at the top, we have a really complicated equation. And so just make a note that that is the equation. If you were doing this by hand, that you would be plugging all your data into. And so again, first we would sort the observations in order of increasing size. We would let our x1 be the smallest value in our sample, and x2 would be the second smallest, and so on. And then the value of W again is given by this equation, where the X with the line over it, big X with the line over it, is our mean of our observations, and then the A subscript I, so little a subscript little I values are complicated. Okay, so if we had 100 values, that would be a lot of math. If we have 20 values, that's a lot of by hand calculations. So we're not going to worry about plugging into this equation. We're just going to use the software and check the box. The computer it's coded to do that for us. So let's keep going here. So unlike most of the test statistics that we're going to encounter in this introduction section, it's actually the small values of the capital W or big W that would indicate a departure from normality. So the capital W statistic, it has a maximum value of 1, which occurs when the data look perfectly normal. The smaller the value of our big W, the less normal the data would be. So let's see. We're going to keep going on page 27, and we're going to look at figure 9.20. This represents the sampling distribution of a big W for a normally distributed data set. And we can actually see that for one of the lines, the non-dashed line, we have big N equals 10. For the bold dashed line, we have N equals 20. And for the very small dashed line, we have N equals 50. And again, in this figure that we can observe on page 27, figure 9.20, this is our sampling distribution example of the Shapiro-Wilk big W statistic, and under the null hypothesis that the data set would be normally distributed for sample sizes of 10, 20, and 50. So again, in figure 9.20, notice that as the sample size gets larger, then the sampling distribution becomes more tightly clumped near our W equals 1. And so as a consequence, for larger samples, our big W doesn't have to be very much smaller than 1 in order for the test to be significant. This is a major drawback of using the Shapiro-Wilk test with larger sample sizes. So like if your sample size is large, even a small departure will be detected as being statistically significant. So when your sample size is large, it is recommended to also verify the histogram and the QQ plot before you determine if the data are not normal. There is a note here, so you could either do that or you could do the Kolmogorov-Smirnov test, which is probably more traditional than the Shapiro-Wilk test. Although most things that we will read seem to suggest that the Shapiro-Wilk is the better test of normality, the Kolmogorov-Smirnov, it's a general purpose test of distributional equivalence that can be adapted to handle other kinds of distribution tests. And in JASP, we're going to use the Shapiro-Wilk test because that's preferred in this software. We're moving on to page 28. So to get the Shapiro-Wilk statistic when you conduct your t-test in the JASP statistical software, we're going to go under the assumption check. So let's just look really quick here. And we're actually going to use a different data set. So hold on, let me open up the we're going to go back and we're going to open up the Chico data set, and this had the two different grades on test 1 and test 2, and we're going to go under our paired samples t-test, and we're going to move our variables over. We're going to see how we can play around with our data. So under assumption check right here, let's look there. And so for this example where we had the really tough professor, Dr. Chico, and we were taking a look at the comparison of how students did on test 1 versus test 2. And if we look under the assumption check heading, we can then see normality, and so we could go ahead and click normality and see what types of data we get for the Shapiro-Wilk test. And it reports that for this paired samples t-test, we have a big W of 0.966 with a p-value of 0.678. And so again, it's telling us that this significant result does suggest a deviation from normality. And then we had the other example that was being provided on page 28, where they ran the normal data set with the n equaling 100 that we used in the past. And for that data set, they got something similar. We don't have that data set, but they got a W of that data set equaling 0.99. Ours was 0.97. And so their p-value was 0.69 and ours was the same. So essentially the output is pretty much exactly the same, even though we only had 20 values in our paired samples test and they had 100. So there is a note here that when they ran the normal sample of the n equaling 100, they said that it was not a surprise that they had no evidence that the data departed from normal, and so that when reporting the results for the Shapiro-Wilk test, they advised that we would want to, as usual, make sure to include the big W test statistic and the p-value. Though given that the sampling distribution depends so heavily on the big N value, it would probably be polite to also include the big N as well. And so they want us to do one more example where we use the AFL small margins data set. So let's do another one. So we're going to open up the small margins data set, if it's still here. Nope, it's in our downloads. Let's have a little fun and do one more example. So here it is, small margins data set, open. Give it a second to open. There we go. We'll maximize this and let it do its thing. There it is. There's our small margins data set. So here we go. We are on page 28. We're in example 9.7.4. So yes, we know it's worth showing another example of what happens to the QQ plot in the Shapiro-Wilk test when the data turn out to be non-normal. And so for that, we're going to look at the AFL winning margins data in the AFL small margins CSV file. And so we're going to go ahead and we're going to plot the histogram of this data. So we remember how to do that. So we go under descriptives, we open up descriptives, statistics, and we're going to move our margins data into the variables box. And we're going to let it do its thing. There we go. So it took a little while because there's 176 values that were reported. The mean was 35.3, standard deviation 26.07, with a max of 116. So we go under our basic plots, and then we do the histogram, which is the distribution plot, and we can also display the density. So give it a second to do that. Yep, looks exactly the same as the figure on 9.21. So as we can see, we have our AFL margins data, and it goes from 0 to 120, and we have a positively skewed data set. Yep, so there we go. We're on page 28 and it matches figure 9.21. So we have the moderately positively skewed data set. We're going to keep going, and then we're also going to plot the QQ plot. So we're going to check this box here and compare. Our QQ plot to the figure on page 28, which is figure 9.22. So let's take a look. There it is. So it goes from -3 to +3. Yep, for theoretical quantiles. Sample quantiles goes from -100 to 150. And let's go to page 29. So given this clear skewness, we wanted to, of our histogram, we wanted to see how the QQ plot was impacted. So then we made our QQ plot of these data, and we can note that the points on the ends here and here, they do deviate from the straight line, right? And this signifies that the data are not normal. So when we run the Shapiro-Wilk test on this AFL margins data, we're going to get some values. So let's see if we can do that. So we're going to check Shapiro-Wilk test. We're going to go back up here, and we're going to see what our value came out to be, and if it matches what's on page 29. So it says when we run our Shapiro-Wilk test, which we just check a box, right here, check the box. On this AFL margins data, we get a value of the for the Shapiro-Wilk normality test statistic of big W, okay, equals 0.940. So that matches what's on page 29, and our p-value is p-value of our Shapiro-Wilk test is less than 0.001. That matches as well. So because this p-value is less than the standard of our 0.05 alpha level, we will reject our null hypothesis. A statistically significant Shapiro-Wilk test does tell us that there is evidence that the population from which our sample was randomly drawn was probably not normally distributed. And so the next section that we're going to look at is going to be section 9.8, which is on page 29. And we're going to get into non-parametric alternatives. So we're going to be talking about the Wilcoxon signed rank test and the two-sample test, which is the Mann-Whitney test. So take a pause here